Welcome to Chapter 1, Section 8, the Appendix. This is one of the most important sections in the entire book, where we actually construct the real numbers from the rationals. In Theorem 1.19, Rudin stated that there exists an ordered field with the least upper bound property. Now we prove it, step by step, using the elegant method of Dedekind cuts. Here is the roadmap for this appendix. We will go through the construction in 9 steps, starting with the definition of Dedekind cuts, then building up the order structure, the least upper bound property, addition, multiplication, and finally the embedding of the rationals into the reals. Let's get started. Before we dive in, let's recall exactly what we are trying to prove. Theorem 1.19 makes 2 claims. First, that there exists an ordered field with the least upper bound property, and second, that the rationals sit inside it as a subfield. We accepted this on faith earlier, but now we will construct such a field explicitly. So far in this chapter, we have been working with the real numbers as if they exist. Theorem 1.19 claimed that there is an ordered field with the least upper bound property, but we never proved it. This appendix fills that gap. Let's outline the strategy. We are going to actually build the real numbers out of the rationals. This is not just an abstract existence argument. We will define specific objects, called Dedekind cuts, and equip them with addition, multiplication, and order. And the method has a name. The tool we use is called a Dedekind cut, named after the German mathematician Richard Dedekind, who published this construction in 1872. Around the same time, Georg Cantor independently gave a different construction using Cauchy sequences. Both approaches achieved the same goal, filling in the gaps of the rational number line. Let's see how cuts work. The construction proceeds in 9 steps. In the first 2 steps, we define what a cut is and how to compare 2 cuts. This gives us an ordered set. Next comes the key property. Step 3 is the heart of the construction. We show that the ordered set of cuts has the least upper bound property. This is the whole reason we use cuts. They are designed to fill the gaps in the rationals, but an ordered set is not yet a field. Steps 4 through 7 equip the set of cuts with addition and multiplication, turning it into an ordered field. Addition is defined in detail. Multiplication requires a bit more care because of signs. And finally, we need to connect the rationals to this new field. Finally, steps 8 and 9 show that the rationals sit naturally inside the reals. Each rational number RR corresponds to a specific cut, and this correspondence preserves sums, products, and order. This is why we can regard the rationals as a subfield of the reals. Let's begin with step 1. Here is the central idea. Think of the rational number line. A Dedekind cut is a way of slicing this line into 2 pieces, a left piece and a right piece. The left piece, which we call alpha, is the cut itself. Every rational p in the cut is less than every rational q not in the cut. The beautiful thing is that the dividing point does not have to be a rational number. This is exactly how cuts capture irrational numbers, like the square root of 2. Let's make this precise. Here is an honest question before we start. Why would anyone think a subset of the rationals is a good way to represent a real number? The motivation is that a real number is determined by the rationals below it. If you know exactly which rationals are less than x, you know x. So we cut out the middleman and simply declare the real number to be the set of rationals below it. The three axioms we are about to list just pin down what it means for a set to be all rationals below some invisible point. Property 2 rules out pathological subsets like the even rationals or rationals with prime denominators. Such sets would have holes scattered everywhere and would not correspond to any point on the number line. Downward closure is what forces a cut to look like a solid ray, stretching all the way to negative infinity, which is exactly the geometry we want. Property 3 is subtle but essential. It is a technical convention that prevents every real number from having two different cut representations. Without it, the number 2 could be represented either by all rationals strictly less than 2, or by all rationals less than or equal to 2, forcing the cut to have no maximum picks the first option consistently, so each real number corresponds to exactly one cut. Notice these are just contrapositives of the definition, not new content. We mention them explicitly because they will be invoked constantly and silently in every proof to come. Whenever you see a step like pick something inside the cut and something outside, so the inside one is smaller, that is this lemma in disguise. Getting used to this move now will make the later proofs feel natural instead of tricky. This example is the whole point of the construction. Remember, example 1.1 at the start of the chapter. We proved there is no rational whose square equals 2, and this created a gap in the rationals. The cut on the slide plugs that gap directly. Notice something curious. We never mention the square root of 2. We define the cut using only rational arithmetic and the inequality p squared less than 2. The irrational number emerges for free as the shape of the cut itself. This is the magic of Dedekind's idea. We get irrationals without ever having to refer to them. Here is the elegant economy of the construction. We do not have to define an order on the reals because set inclusion already gives us one for free. A smaller real number reaches less far to the right on the number line, so its cut contains fewer rationals. Order is not an extra structure we add. It is already encoded in the subset relation. This is a recurring theme in mathematics. The best definitions make the hard work disappear, but we still owe a proof that inclusion actually satisfies the ordered set axioms. Transitivity is free because subset inclusion is already transitive for any sets whatsoever. It has nothing to do with cuts. We get this axiom without paying anything, which is the kind of bonus you hope for when your structure is built from well-chosen pieces. This clause is also a freebie from set theory. The real work is trichotomy, proving that at least one relation must hold. For general sets, this would be false. Most pairs of sets are simply incomparable. What forces comparability here is the very specific shape of a cut, and the next slide is where we finally have to use that shape. Trichotomy is where we have to do actual work. The claim is that any two cuts are always comparable. Pause to appreciate how surprising this is. Arbitrary subsets of the rationals are almost never comparable by inclusion, but our cuts always are. Something special about the axioms is doing the job. The strategy is a dichotomy. Either alpha is contained in beta, or it is not. If it is, we are done. If it is not, we show that beta must then be contained in alpha. There is no middle ground where the two cuts overlap partially. Why? Because a single witness, P in alpha, but not in beta, acts like a wall. Every element of beta is forced to sit to the left of P, and downward closure then sucks every such element into alpha. One escaping point drags the whole cut along with it. This leveraging of a single witness is a very common proof move. It is worth remembering. The formal version just spells out the previous picture. Pay attention to the logical structure, not the symbols. We started by ruling out 2 of the 3 possible orderings, and the one witness P forced the third to hold. That is how trichotomy proofs are typically organized. Assume 2 cases fail, and show the third is inevitable. With this, the set of cuts is an ordered set, and we can move on to its most important structural property. This is the payoff for all the care we put into defining cuts. Here is why the union works intuitively. Each cut in A is a shaded region reaching leftward from some invisible boundary point on the number line. When you overlay all of them, the result is the shaded region reaching to the rightmost boundary among them. That rightmost boundary is exactly the supremum. The great surprise is that you never have to construct the supremum. You just take a union, and set theory does the rest. Compare this with the rationals, where no such operation would give you a rational answer. The cut formalism is specifically engineered so that unions stay inside the system. Notice how essential the boundedness assumption is here. Without the upper bound beta, the union could in principle swallow all of the rationals and fail to be a cut. The upper bound acts like a ceiling that confines the union, guaranteeing it stays a proper subset. This is why the theorem requires bounded above, not just for the conclusion, but for the construction to even make sense. Downward closure is inherited automatically. Each piece of the union is already downward closed, so their union is too. This is a general principle worth noting. Unions of downward closed sets stay downward closed, and unions of upward closed sets stay upward closed. Intersections, by contrast, also preserve these properties, but unions and intersections behave very differently with respect to proper subset comparisons. The no maximum property also transfers up from the pieces to the union for free, and the same general principle applies. A union of sets, each without a maximum, cannot have a maximum itself, so all 3 cut axioms are inherited almost automatically from the members of A. The real creativity went into designing the axioms. Once the axioms are right, verification is mostly bookkeeping. The upper bound part is trivial by definition of union. The least part is where the cut formalism really pays off. The logic to focus on is this: to show gamma is the smallest upper bound. We assume someone offers a smaller candidate delta, and we expose it as inadequate by finding an element of A that escapes above it. That escaping element comes from a single rational S witnessing gamma not equal to delta. Once again, a single point does all the work. A recurring pattern you should start noticing. Pause on one subtlety the diagram hides. When A is an infinite set of cuts, none of them may individually reach all the way up to the supremum. The members may only approach it from below, the way 1 over n approaches 0 without ever touching it. The union still captures the sup exactly, because a rational P lands in the union if it is in at least one member, no matter how late that member appears in the enumeration. This is why the construction works even for supremums that are not achieved by any single member of A. This definition is the obvious one, but it is worth asking why. If cuts represent real numbers, and addition of real numbers should correspond to pointwise shifting of boundaries, then the sum of cuts should be obtained by sliding the left-hand piece rightward by as much as the right-hand piece reaches. Taking all pairwise sums achieves exactly that shift without ever mentioning the boundary points directly, which is good, because the boundary points may not even exist as rationals. As for 0 star, it is the set of rationals strictly less than 0, with 0 itself excluded because of the no maximum axiom. Here's the geometric picture. If alpha is the cut at some point A, and beta is the cut at some point B, then alpha plus beta is the cut at A plus B. We take all possible sums of a rational from alpha and a rational from beta, and these sums fill out everything to the left of A plus B. Of course, we need to verify that this set is actually a cut. The clever move here is the second half. To show the sum cut is not all of the rationals, we build an explicit ceiling witness. We grab a rational above alpha and one above beta, and their sum acts as a ceiling above alpha plus beta. Why does that work? Because sums of smaller things stay smaller than sums of larger things. A trivial fact about the rationals, but it is exactly what lets the cut property propagate from the inputs to the output. If addition did not respect ordering, this whole construction would collapse. The trick is to keep S fixed and absorb the shrinkage into the alpha side. If we want a smaller sum Q, we can write Q as Q minus S plus TS, treating S as a rigid anchor and letting the first piece shrink into alpha via downward closure. This asymmetric move, freeze one factor, vary the other, appears repeatedly in cut arguments. It works because both alpha and beta are downward closed, so we only need to exercise that property on one side. Notice how property 3 of the sum piggybacks on property 3 of just one of the summons. We never even touched beta. Whenever you need to push up slightly above a given element, pushing up the alpha side is enough. This asymmetry is fine, and it shows that the cut axioms are more than we strictly need at each step. There is redundancy built in, which makes proofs easier. Commutativity and associativity come along for the ride. They inherit from the rationals without any thought, because cut addition is defined as pairwise rational addition. The interesting axiom is A4. Why is the identity slightly tricky? Because alpha plus 0 star is not literally alpha. It is a set of sums R plus S with S negative. It takes a little argument to show this set is exactly alpha, and the clever step is the reverse inclusion. Given any P in alpha, we decompose P as R plus negative number, where the larger R exists because alpha has no maximum. This is the first place we use axiom 3 in a non-trivial way. The trickiest axiom is the existence of additive inverses. Given a cut alpha, we need to find a cut beta, such that alpha plus beta equals 0 star. Here is the high-level idea. The complement of alpha consists of all rationals that lie at or above its boundary point. If we flip that complement across 0, we get exactly the rationals that lie at or below the negative of the boundary. That flipped set is almost minus alpha, but we do not want the boundary point itself to sneak in. This is why the definition introduces a positive buffer R. By requiring minus P minus R to be outside alpha, we force minus P to sit strictly beyond the boundary, not on it. so P is in beta, exactly when some rational, strictly less than minus P, fails to be in alpha. This beta is the additive inverse of alpha, denoted minus alpha. This diagram makes the definition of the additive inverse concrete. On the lower number line, you see the cut alpha in blue, ending at some boundary point. On the upper number line, you see beta equals minus alpha in green, and the dashed vertical line at 0 shows the mirror symmetry between the two cuts. Now focus on the point minus P on the lower line. It sits strictly to the right of alpha, and minus P minus R also sits outside alpha, confirming that minus P is safely beyond the boundary by a buffer of size R. Reflecting across 0, the point P lands on the upper line strictly inside beta. That buffer R is the key. Without it, P could land exactly at the boundary of beta, giving beta a largest element and ruining the cut property. Now let's verify that beta is indeed a cut. We verify beta is a cut. For property 1, pick any S not in alpha and set P equals minus S minus 1. Then minus P minus 1 equals S, which is not in alpha, so P is in beta. Thus, beta is non-empty. Also, if Q is in alpha, then minus Q cannot be in beta, because every rational less than Q is already in alpha, contradicting the definition of beta. So beta is not all of the rationals. For property 2, if P is in beta and Q is less than P, then minus Q is greater than minus P, so the same witness R works for Q. For property 3, given the witness R, we take T equals P plus R over 2, which is strictly greater than P and still in beta with witness R over 2. Now we must show that alpha plus beta equals 0 star. We show alpha plus beta equals 0 star in 2 parts. The forward inclusion is clean. If R is in alpha and S is in beta, then minus S is not in alpha, so R is less than minus S, which gives R plus S less than 0. For the reverse inclusion, here is the high-level idea. Given a negative rational V, we want to write it as a sum of something in alpha and something in beta. The trick is to split V symmetrically as V over 2 plus T and V over 2 minus T for some cleverly chosen positive T. We want the first piece to land inside alpha and the second piece to land inside beta. To find this T, we use the Archimedean property. Set W to be minus V over 2, which is positive. The Archimedean property gives an integer n such that n times W is in alpha, but n plus 1 times W is not. This n marks the boundary of alpha on the lattice of multiples of W. Now take T equal to n plus 1 times W. Then V over 2 plus T simplifies to n times W, which is in alpha, and V over 2 minus T equals minus n plus 2 times W, call it P. To check P is in beta, note that minus P minus W equals n plus 1 times W, which is outside alpha, exactly the witness beta requires. So V equals n times W plus P belongs to alpha plus beta. This completes the proof that beta is the additive inverse, which we denote minus alpha. This diagram visualizes the clever splitting. On the bottom number line, we see the cut alpha in blue extending to the left up to its boundary. On top, we see beta equals minus alpha in green, extending to the left up to the mirror image of that boundary across 0. The Archimedean property gives us an integer n, such that n times W lands inside alpha, shown as the blue dot, while n plus 1 times W lands just outside, shown as the brown dot. These two lattice points bracket the boundary of alpha from both sides. Now pay attention to the midpoint V over 2 shown on the lower line. The two braces above the line show that Va over 2 is equidistant from NW on the right and from P on the left. At distance exactly T equals in plus 1 times W. In other words, V over 2 plus T equals in W, which lives inside alpha, and V over 2 minus T equals P, which lives inside beta on the upper line. Adding these two pieces recovers the target V, so V has been exhibited as the sum of something in alpha and something in beta, exactly what we needed. This is the compatibility axiom that turns an ordered ring into an ordered field in the sense of definition 1.17. The interesting question is not that the proof is short, it is why it is short. The answer, inclusion between cuts, really is the order, and union-like operations preserve inclusion automatically. Once we know cancellation, getting strict inequality, instead of just weak inequality, is immediate. Contrast this with what happens if you try to verify the same axiom on the Cauchy sequence construction of the reals. It is much messier there. As a consequence, a cut is positive if and only if its additive inverse is negative. With the addition axioms verified and order compatibility established, we have confirmed the first requirement of definition 1.17. Now we need to handle multiplication, which is the subject of the next two steps. A warning about why multiplication is harder than addition. For addition, the pairwise sum idea works uniformly because sums of smaller numbers are always smaller. Addition preserves order with no exceptions, but multiplication flips sign. Multiplying by a negative reverses order. So the naive pairwise product set would not even be downward closed if negatives were allowed. The standard dodge is to define multiplication first on positive cuts, where order is preserved, and then handle signs by hand in step 7. Another small detail. Notice the definition uses P less than or equal to RS, not strict, to ensure downward closure works cleanly. Rudin skips these proofs because they are mechanical repetitions of the addition arguments, but it is worth mentioning what is different. Multiplicative inverses are the one genuinely novel step. You have to invert the boundary point of alpha across 1 rather than across 0, and the same buffer trick from the additive inverse reappears. If you sit down to do the work yourself, expect the inverse axiom to be harder than all the others combined, the same way it was for addition. This is the rule of signs definition, imposed by hand rather than derived from a general construction. It feels ad hoc, and in a sense it is, but there is no better option. Any definition of multiplication that handles negatives uniformly would require the sign-flipping property to be derivable from something else, and when you are constructing the reals from scratch, there is nothing else yet to derive it from. The lesson is that the familiar negative times negative equals positive rule is not a fact about numbers. It is a choice that makes the distributive law hold. Why does case analysis work here at all? Because the distributive law in the positive case, which we already know, propagates outward through all the sign combinations via the identity that negation commutes with multiplication. In other words, the whole field structure on R is bootstrapped from the positive cut calculations in step 6. This is a nice instance of a general technique. Prove the theorem in the simplest regime, then use symmetry to extend. Steps 1 through 7 now deliver everything Theorem 1.19 promised about existence. All that remains is the embedding of the rationals. There is a potential for confusion here. The rational number r and the rational cut AR star are not the same thing. R is a number, R star is a set of numbers, but they will behave identically under addition, multiplication, and comparison, and that is all the algebra can see. This distinction matters philosophically, but becomes invisible in practice, which is exactly why we can afterwards pretend that the rationals live inside the reals. Also note why the no maximum axiom forces the strict inequality. If we allowed P equals R into the cut, it would be the largest element. And this is the step that promotes the map R goes to R star from a mere bijection to a genuine homomorphism. The forward inclusion is trivial. The reverse is the interesting direction. And the trick is that when P strictly undershoots R plus S, we have positive room to spare, namely the gap T. We split that gap evenly between the two sides, and both halves land safely inside their respective rational cuts. Dividing the slack in half is a small move, but it is the heart of the proof, and it only works because the rationals are densely ordered. The second property says that multiplying rational cuts corresponds to multiplying the rationals. The proof follows the same pattern as part A. The third and final property concerns order. The key witness in the forward direction is R itself. It is strictly below S, so it lives in S star. But it is not strictly below itself, so it is not in R star. That single rational separates the two cuts, proving proper containment. In the reverse direction, we again use a single witness to translate a set theoretic statement back into an inequality on rationals. With these three properties, we can stop distinguishing R from R star. The embedding is faithful in every way we care about. Step 9 puts everything together. The rational cuts form a subset of R that behaves exactly like the rationals. Addition, multiplication, and order all match up, while R star is technically a set of rationals, not the rational number R itself. All the algebraic and order properties are identical. This is what isomorphic means. From now on, we can safely identify each rationalist R with its cut R star, and think of the rationals as sitting inside the reals. A remarkable fact, which Rudin states without proof, is that any two ordered fields with the least upper bound property are isomorphic. This means there is essentially only one such field, the real numbers. Our construction via Dedekind cuts is one way to build it. Cantor's construction using equivalence classes of Cauchy sequences is another. Both were published in 1872. The two approaches are quite different in flavor, but they produce isomorphic results. Let's review the key ideas from this appendix. First, a Dedekind cut is a subset of the rationals satisfying three simple properties. It is non-empty and proper, it is closed downward, and it has no largest element. And the key consequence of this definition is next. The set of all cuts, ordered by inclusion, automatically has the least upper bound property. The supremum of a bounded set of cuts is just their union. This is the central insight of the construction, but we also needed arithmetic. By defining addition as pairwise sums and multiplication carefully by cases, the set of cuts becomes a full ordered field, and the final piece of the puzzle is the connection to the rationals. Finally, Every rational number corresponds to a rational cut, and this correspondence preserves all arithmetic and order. This completes the construction of the real numbers and the proof of Theorem 1.19. With the real number system firmly established, we are ready to move on to Chapter 2, where we study the topology of metric spaces, including the crucial concepts of open sets, closed sets, and compactness.